All right, so picking up where we left off, I was talking about dipoles and what it takes to actually have a polar molecule. And right now, we're only going to be talking about the bonds themselves. We'll talk about the geometry of the molecule later when we talk about VSEPR and whether or not there's symmetry or no symmetry, or how that works. So right now, we're only talking about bonds. And whenever you have a polar covalent bond, like let's say you have water, this bond is polar, and it causes the oxygen to have a slight negative charge and the hydrogen to have a slight positive charge. And these aren't whole number charges, these are like partials, like 0.66 negative, and this is 0.33 positive, and this is positive 0.33. So it balances out still, but there is still kind of this electron hog down on this end, and these guys are pretty electron deficient on the other end. So when you draw a Lewis structure, these are the 5 points, or the 5 steps that you need to follow. I suggest you pause this and write these down because you're going to need them. I'm not really even going to talk about these. A little bit. Add its total valence electrons, and basically put the central atom in the middle, and then put the other atoms around it and bond them. And usually the central atom is the least electronegative. And then you complete the octets around the outer atoms by putting dots. And any leftover electrons that you have, put them on the central. And if there's not enough electrons to give the central atom an octet, that's when you have to make multiple bonds. And as we work out examples of these, it'll make more sense. So we're going to draw the Lewis structures for these 4 compounds. Starting with the nitrate ion, NO3. Well, we've got 1 nitrogen, and nitrogen has 5 valence electrons, and each oxygen has 6, so that's a total of 18, which gives us 23 electrons that we need to deal with, plus this negative gives us 1 more, so that's now 24 electrons that we need to deal with. So put the N in the middle, put the oxygens around, single bond them, and then complete octets. So this bond right here represents 2 electrons, so each oxygen needs 6 more, like this. So now count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Excellent. And now because this one is charged, we put brackets around it with the negative on the outside. So that's that one. Then doing CO2. Carbon has 4 valence electrons, and each oxygen has 6, so 2 times 6 is 12, plus 4 is 16 electrons. Carbon goes in the center, oxygens go off the side. Complete the octets out here. And let's count out the electrons. 2, 4, 6, 8, 10, 12, 14, 16. So that works. But this doesn't put enough on the carbon. You notice carbon only has 2, 4. So we need to get rid of a pair here, make a double bond. Get rid of a pair here, make a double bond. Carbon always has to have 4 bonds. And so now we got 2, 4, 6, 8, 10, 12, 14, 16. Everybody has an octet, so everybody's happy. PCl5. Phosphorus has 5 valence electrons, plus 5 times chlorine's 7 valence electrons gives us a total of 40 that we need. Phosphorus is going in the center. Chlorine, I just kind of try to evenly space them around. And then bond them all in. Phosphorus is one of those special ones that you can actually have something bigger than an octet, and we'll talk a little bit more about that in a second. I'm just going to put my dots on my chlorines. Just putting some dots on some chlorines. Okay, now I'm going to count all these up and see if I need to add any more on phosphorus. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Awesome. 40 electrons is what we wanted. Oops, sorry. Okay, last one we're going to do NO3 without a charge. So this up here was the nitrate ion. This right here is the nitrogen trioxide. But now since, this one had 24 electrons, this one goes back to having 23. The 5 from the nitrogen plus 3 times the 6 from oxygen adds up to 23. So nitrogen still goes in the middle. Oxygens go around. Single bond them. Dots. And count them up. 2, 4, 6, 8. 10, 12, 14, 16. 18, 20, 22, 24. We've got one too many. And we only have 6 bonds here, so let's knock that out and double bond it here, and that's still 24, so it's still one too many. So we're gonna knock a random one off. This will make more sense, so we're gonna take that one off. But what if maybe we should put the double bond here and make this one a single bond? Or why not put the double bond here and have these guys be single bonds? There are 3 equally good places for that double bond. I wonder what that means. There is this lovely little thing called a resonance structure, and this is used when there's more than, not nitrate ion, I'm sorry, I'm getting ahead of myself. This is for NO3. Using 2 or more Lewis structures are equally good representations of the bonds. The actual structure, kind of like an average, so we had the N, O, 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 and it's kind of like, okay, they all definitely have at least something that's like a single bond, but then they kind of share this double bond. And so it's almost like a hybrid, but not quite. And examples, you have ozone and you've got the nitrate ion that all do this. Exceptions to the octet rule: when you have an odd number of electrons like we had with the NO3, then one atom's only going to have 7 electrons around it, and it was one of the oxygens on that NO3. If the compound's a group 2 or 3 element as a central atom, like if we had boron trichloride, then the number of electrons around this central atom is going to be twice the group number. Boron's in group 3, so it only actually needs to have 6 electrons around it instead of the 8 that the octet rule says it should have. So boron trichloride would look like this, with the dots around the chlorines. And then if the central element is big, like when we did PCl5, it can have what's called an expanded octet, which means it just has more than 8. And phosphorus and sulfur are really notorious for doing this. Covalent bond strength: multiple covalent bonds are stronger than single covalent bonds, and they're also shorter. So if you had, let's say CCl4, these are all single bonds, and then the carbon dioxide was a double bond. This bond is stronger and shorter than this single bond, and then triple bonds are even stronger. So the higher the number of electrons shared, the stronger the bond. So like here we're sharing 4 electrons, here we're only sharing 2, which is why this one is stronger. These are the practice questions that I want you guys to go through. You should be able to do most of these. There's a couple of delta H ones in there that you'll need to check out the information in your book. I'm going to add some, this is not all of the notes. I'm going to add to the notes and do some of the delta H with the bond stuff on Monday, as well as start going through Vesper, because that's the little chunk of chapter 9 that we need to get to. So if you guys have any questions, ask Mr. J. He'll help you if he can, and if not, you can email me if it's like absolutely pressing. If not, save it for Monday, and I'll see you guys when I get back. Have a good weekend.